Okay, now we want to take a look at using the integral to calculate volumes of solids of rotation. And we're going to do this using several methods, but today we're going to use one method which is called the disk method, which is used when your region is bound by its axis of rotation. You'll see what that means as we get going. So let's jump into an example. It says, find the volume of the solid formed when the region bound by the graph of y equals x squared, which you see there in red, the line x equals 1.5, which I'll draw in here in green, and the x-axis, so here's another boundary, so I have this kind of wedge-shaped region, I'll label it region R, okay, is rotated about the x-axis. So we're going to 360 degree rotate that region about the x-axis. It would form a solid if you did that. So you can imagine this is like an engineering design. You could do a two-dimensional sketch and then be able to ask yourself, okay, if I built this, what would its volume be? And that can be an important question in design because you may not have enough material to build this object, or maybe too expensive, or whatever other restrictions you may have. Now, it takes a while for some of us to visualize what these solids look like, because we're trying to represent a three-dimensional solid with a two-dimensional picture. That's hard to do. So before we go about how to calculate the volume of the solid, I'm going to try and show you what it actually looks like using a simulation. So let's go ahead and jump into a program called WinPlot that'll help us see this more effectively. Okay, so we're here in WinPlot, and you can see the red curve y equals x squared, the blue line segment, which is going to represent x equals 1.5, as a boundary, and we're going to ask WinPlot to do a rotation. And when we do this, we should see more or less what the solid would look like when rotated about the x-axis. So let me put some axes on here, and we get a three-dimensional representation of what this solid would look like. Okay, so hopefully you can imagine you're going to get kind of a funnel-shaped or a tornado-shaped figure. And it would be solid, it would be filled in, not like what you see here in this picture where there's no top to it. Okay, but I'm going to try to show it to you from several different angles so you can kind of get a feel for how the curvature defines the boundaries of the solid and how the line x equals 1.5 determined how high up we go or how far to the right you want to go depending on your perspective. Okay, but that's an example of what a solid rotation might look like, and you need to kind of visualize how the two-dimensional picture becomes this three-dimensional solid that we're going to try to find the volume of. Okay, so back to the procedure of how we're going to actually find the volume of that solid. Again, we're going to start with a representative rectangle in the region. I told you in this unit you're going to draw a lot of rectangles. It's a good practice because it'll avoid helping us make mistakes down the road. So a rectangle that's going to be in the region, and it's going to get rotated about the x-axis would look like this. I want to label some coordinates, so in general I could call the coordinates down here x comma 0, and up here x comma f of x, which is x squared, and the width of this rectangle is an arbitrary dx. Now, I want you to imagine that that rectangle is being rotated 360 degrees around the x-axis. Okay, what shape would be created? You may be able to visualize that, but I'm going to go ahead and show you with another simulation what that would look like, and then we'll come back and calculate the volume of this particular shape, and that'll help us set up an integral to do the volume of the entire region. Okay, so we're back here in WinPlot, and so you can see here I have a rectangle that in this case is touching the y-axis. It doesn't really matter, it's the same principle, but we're going to be able to, using this slider bar, rotate that rectangle 360 degrees around the y-axis, which is similar to the problem we're about to do. And you probably already guessed, but when you rotate this rectangle, the solid that gets formed is a cylinder. And in calculus, we're going to call this figure a disk because it's a cylinder that's very, very thin. Okay? Think like a penny or a dime. When we add up a bunch of these disks, it will form the volume of the entire solid because they are so thin that you don't see any ridge to them. Okay? So I can rotate this figure a little bit so you can see it from different angles, but basically what we end up doing here is taking the volume of a generic disk and doing an integral of that volume, and that gives us the volume of the entire solid. So the general procedure kind of stands up like this. We draw a representative rectangle, and we understand that that rectangle becomes a cylinder, and the volume of a cylinder is pi r squared h volume of a cylinder. And now we just need to be able to assign in our picture the parts that get represented by R and H in the volume of cylinder formula. So if I look over here at the cylinder that gets formed when you rotate a rectangle about the x-axis, I can see that the radius is the length that goes from my curve down to, in this case, the x-axis. Okay, but I'm going to say in general that the radius is the distance from our curve to the axis of rotation. Because the axis of rotation won't always be the x-axis, it might be the y-axis, or it might be another line. So I just want to say that in general. Okay, and then the height of this cylinder is this little distance here. And so I'm going to say that the height is going to always be the arbitrary dimension of our rectangle. So that's the dx or the dy, depending on which way we draw our rectangles. So if we just follow this procedure, we should always be able to set up an integral to find the volume of a solid of rotation. We just have to figure out, okay, what is the radius in this picture of the cylinder and what is the height? So let's go back to the problem we've been working and apply those procedures to figure out what role these different dimensions play here. So I have a rectangle. The height of this rectangle is the distance from my curve down to the axis of rotation. So the radius of my cylinder that's going to get rotated is going to be x squared minus 0, or just x squared. The height of my cylinder is going to be the arbitrary dimension of this rectangle, which is dx. And so the volume of a generic cylinder in the region is going to be pi times the radius, which is x squared, times dx. Now, I want to add up every cylinder in this region and make them extremely thin, and that'll give me the volume of the solid that we showed you a while back. So that's going to be done with an integral. So the integral is going to go like this. I'm going to integrate the same volume formula. So if I clean that up a little bit, it's pi x to the fourth dx, and my limits of integration are going to go from the left boundary to the right boundary. The left boundary is the point 0, 0, and the right boundary is the point 1.5, or x equals 1.5. So those are x boundaries here. And so if I can evaluate this integral, I'll have the volume of the solid we showed you a few slides back. So let's go ahead and do this. The pi can come out as a constant, so I can focus on the function that's actually in here, which is x to the fourth dx. Okay, I can write the antiderivative as 1/5 x to the fifth. And I'm going to evaluate at 0, and I'm going to change the 1.5 to 3/2 because fractions are going to be easier to deal with here. Okay, so again, I like to have big parentheses with a subtraction sign to keep my work straight. So I have, let's write it like this, pi over 5 times 3/2 to the fifth. And then this second one is going to be 0. And so now we can just write down the final answer. 3 to the fifth is 243. So we have 243 pi divided by 2 to the fifth is 32, and 32 times 5 is going to be 160. So believe it or not, the volume of that figure we just showed you, that tornado-shaped figure, is going to be exactly 243 pi over 160. Okay, let's look at another example. Here we're going to find the volume of the solid formed when the region bound by the same curve, y equals x squared, but this time we have a horizontal line, y equals 9/4, which I'll draw in here in green, is rotated about the y-axis. Okay, and we should probably also mention that the y-axis is a boundary for this region here. That should probably be noted there. Okay, so this time we're going to rotate this about the y-axis. This is the point 3/2, 9/4. And before we get into the process here, I want to show you a picture of what this solid will look like. You may have a guess already, but it's not always easy in the beginning to visualize these things, so let's go ahead and show you. Okay, so here's our region again. We have the curve y equals x squared in red, and we have the line y equals 9/4 there in blue. And we're going to ask WinPlot to revolve a surface about the y-axis. And so here is the picture. Let me add the axes here, give us a little bit more perspective. And you might have guessed what it was going to look like. It's going to look kind of like a bullet shape, or a kind of a play arrow shape that you might fire at an archery range. Okay, gumdrop, those kind of things. And again, remember this is going to be a solid. It's not going to be hollow like this one. It's going to be filled in. But we were able to calculate the volume of this solid using calculus. Okay, it's kind of a neat deal. But again, visualizing the solids is not necessarily essential, but I think it helps just to understand what's going on here. But again, it's built up of a series of cylinders that are stacked on top of each other. Cylinders are disks. Okay, so back to the problem. How are we going to find the volume here? Now, if I draw my rectangles vertically like I did on the last slide, I will not be touching the axis of rotation. Okay, the method we have outlined here, volume by disks, has to have your region touching the axis of rotation, which our region is, and our representative rectangles also need to be touching the axis of rotation. So in this case, I must draw my rectangles horizontally to accomplish that. So let's go ahead and draw a representative rectangle. And once again, I want to draw generic coordinates to represent one of the dimensions here. So in this case, the y-coordinates are the same for these two dots. And if I live on the y-axis, my x-coordinate is 0, so that guy is easy to find. I have to find the x-coordinate in terms of y for the red curve, and the red curve is called y equals x squared. So if I solve for x, I get plus or minus square root of y equals x, but I'm in quadrant 1. So I know that if I'm in quadrant 1, my x-coordinate is positive, so the x-coordinate in general is the square root of y. Okay. My arbitrary dimension here is dy. I need to visualize this rectangle being rotated about the y-axis and forms a cylinder, and I need to figure out what role all these things play in the cylinder. So the radius of the cylinder is going to be, follow the procedure that we had outlined a few slides ago, the distance from my curve to the axis of rotation. Okay, in this case, this is the horizontal distance from this dot here to this dot here, which is going to be the square root of y minus 0. The height of the cylinder is the arbitrary dimension, in this case dy, and so that means that the volume of the typical cylinder in the region is found by this formula, pi radius squared, so the radius is the square root of y squared times dy. So to find the volume of the entire solid, we're going to integrate that formula in the region. So we have pi y dy, and my limits will be a y-coordinate of 0 all the way up to a y-coordinate of 9/4. And all we have to do now is integrate this expression, or find the antiderivative of this expression, and plug in our limits of integration. So we're going to have pi over 2 y squared from 0 to 9/4. Again, I like big parentheses with a subtraction sign just to keep things straight. This won't always be a 0 in the second component, sometimes it is. And I'm going to get 81 pi divided by 32 is the volume of our solid.